Here we show a 3D Cartesian grid, orthogonal meaning 90 degrees, so all the directions are orthogonal to one another. This will be X direction, this will be Y, and this will be Z. Going down. They are all at 90 degrees to one another. And this will be delta X, this will be delta Y, this will be delta Z, right? This is a common grid used in reservoir simulation. This is also typically used for single well studies, and this is the radial grid. This is the radial direction as the radius increases. That's R. I already showed this before, right? And this angle can start from here is theta. And of course, this is Z. And this will be delta R, right? This will be delta theta. And this will be delta Z. So that's the cylindrical coordinate system. This is what is typically used in most commercial simulators, and it's a corner point geometry. What that means is you provide the XYZ coordinates of the vertices of the domain, of the grid blocks, and it actually uses pillar gridding, which we won't go into. We'll leave the geologists to worry about this. And the way that works is you basically provide these lines, which are the pillars that start from the top of the model to the bottom. Starts from the top of the model to the bottom. And that is actually what is used to come up with the XYZ coordinates of the corners of each grid block. Because in slopey systems with falls, that approach works very well, because this could be the top, this could be the bottom of one pillar, this could be the top, this could be the bottom of another pillar, right? And you could have those moving all across the system, and it allows you to model pinching out and fault displacements in the reservoir, like here. So this runs from here to here on the left. On the right, why is the color changing? On the right is here. So those coordinates are different for, even though it's the same interface, and that's why we're able to model these displacements or through of the fault. It also allows you to model pinch outs and things like this. So this is the most common grid geometry used in reservoir simulation. You're going to see this in CMG. It also exists in Eclipse, but we're not using Eclipse in this course. Other types of models. We have full field models. So we're starting out with the largest one. This is smaller, and this is the smallest. So in full field models, as you can probably guess, you're going to have a model that contains all of the reservoir sands in the field. And the reservoir, of course, will contain the region of interest, and it can also extend out to these nearby aquifers, because the aquifer can provide can provide some aquifer support, right? Another thing we also model in full field models is surface facilities. So we have some surface facilities. We have a model for how the fluid flows from the bottom of the well to the surface. Was the well bore model, and it's all integrated. And this is very useful, as you can probably guess, to predict how the entire field performs. And it's very computationally expensive, right? Because you will have several grid blocks for the different reservoirs in the field. The window area model focuses on a region within the reservoir. So just a portion of the reservoir is modeled, not the entire reservoir. Talk less of modeling the entire field. It's usually modeled typically with one well or pattern. An example of this could be the five-spot pattern, right? Where you can have either 5-spot or inverted 5-spot, where you can have 4 injectors and 1 producer. And instead of modeling all of these, because this can also repeat, right, in X and Y directions, you have another one here. Instead of modeling even just all of this, you can actually model just a quarter. So you hear the word quarter 5-spot based on symmetry. So the performance of this quarter will be equal to the performance of this quarter, which will be equal to the performance of this quarter, and you can basically model just a quarter of the system and multiply the results by 4. That could be representative of a window area model. There is also the conceptual model, which is even smaller, and that typically uses the cylindrical coordinate system we discussed previously. And you're just focusing on one single well, and you want to understand maybe a pilot study. You want to drill down to just the well, you can use this conceptual model. It's a single well model, and like you can see here is the rate is based on the radial geometry. And here we compare the advantages and disadvantages of these different types of models. One of the advantages of the full field model is the fact that it can use a calibration of the model to observed historical data, right? And that is also a disadvantage in the sense that it takes a lot of work to be able to match all of the observed data for the entire field. It's also computationally expensive. The simulation runs forever. You have several reservoir sands within the field, and it takes a while to simulate all of that. So it consumes computational resources. You can have the effect of interwell cross flow, for instance, and all of those can be modeled using a full field model. That's the advantage. If you're not using a full field model, then you may not see, or you may not be able to account for cross flow between 2 different reservoir sands if these reservoir sands were modeled independently of one another. The advantage of using a window area model, is that you're able to use finer grids. And finer grids means more accurate numerical solution process. right? Because the finer the grid is, the less is the truncation error. And because it's smaller, you are able to get your results in much less time. But it could be challenging to come up with the boundary conditions for the reservoir, like I discussed before, that you're modeling just a quarter in a quarter 5 spots pattern, right? Well, what boundary condition do you use here and here? In some cases, like in this case, it could be very simple. It could be just a no-flow boundary based on the symmetry. In other cases, you might need to account for the boundary fluxes, and those are more difficult. It's not able to account for interwell influences when you're modeling just one well, right? Advantages of the conceptual model is easy, it's fast, it's cheap, doesn't take computational resources. You don't need to do history matching, so less work to be done. And in terms of the cons, the results are at best qualitative. You can't use these to um, determine whether or not you're going to use a recovery mechanism, or you can't use this to plan field development. It doesn't account for observed historical data. So the model may not be representative of the actual reservoir.